Well, some of you were here last time, some of you weren't, but this is what we are dealing with today, and as well as the last lecture. We're minimizing Cx subject to standard form constraints Ax equals b, except that x is bounded below and above by two vectors, L and U. And I'm assuming A is m by n, and rank is also m. And instead of dealing with this, there's too much noise coming. Why don't you open that window? If you wanted to put this problem in the form of x greater than or equal to 0, then you can get rid of one of the bounds, for example, L, by making a change of variables. X, say, substitute x prime equals x minus L, in which case, of course, x less than or equal to u, or u prime, the new version, will not be gotten rid of, so you have to expand the basis. So instead of doing that, we're going to deal with compact basis, which means that we are going to work with basis matrices of size m by m rather than the enlarged one. If you did not follow what I'm talking about right now, the last 1 minute, then you should make sure that you understand that, because that was covered already in the last lecture, and some of you don't seem to be really making the connections. Those of you who are not here will not make the connection, so I suggest that you go over that stuff, because that's the more important part here. Okay? The other is mechanical. You can just derive all the other stuff. The concepts are more important. All right, so at this point, we want to work with basis matrices of size m by m. That's the main motivation here. And we assume some feasible basis B is given. We assume it's feasible. And the non-basic variables, or the A matrix, is partitioned in the form of a basis matrix B with non-basic variables collected in submatrices n1 and n2. n1 corresponds to those variables whose columns, or those columns whose variables are set equal to the lower bounds, and n2 corresponds to the set of columns of the A matrix whose variables are set equal to the upper bounds. And X is partitioned in the same way. So the current basic feasible solution is obtained by taking the variables associated with n1 equal to their lower bounds, and the variables associated with n2 equal to their upper bounds. And finally, xb is obtained by simply solving the system ax equals b by moving the variables that are set equal to lower or upper bounds to the right side. And once you do that, you're multiplying by b inverse the converted right side. So, once you set your non-basic variables equal to their lower or upper bounds, as depending on where they are, then you have a modified right side, and then you multiply by b inverse to get the values of the basic variables. We've gone through this already. And Z bar is, by the way, I gave a name to this. I called it B cap. Okay? That was the name for that. And Z bar, the objective value of the current basic feasible solution is CB times XB bar plus CN1 XN1 plus CN2 XN2 with their current values. And that gives you, of course, CB times B cap plus CN1 LN1 plus CN2 UN2. That's the objective value.
B inverse.
There's no B inverse here. Where's B inverse? Oh,
Value of x is equal to basic x.
the entire thing is B cap.
That's all.
Okay. I think I call this Z cap rather than Z bar. Let me just check my notation here. Yeah, I called it Z cap rather than Z bar. Okay. Okay. So that's our current basic feasible solution and its objective value. So the next question was, how do we improve this if we are able to do that? And of course, if there's no improvement possible, we stop with the optimal solution. Okay. So let me continue here. Let me just continue here. For any choice of xn1 and xn2, rather than the specific choices at the bounds, we may solve for xb and obtain b inverse times b minus n1 xn1 minus n2 xn2. That's what we get. And then, of course, that would give the following objective value as dependent on the choices of xn1 and xn2. What would that be? CB times xb plus cn1 xn1 plus cn2 xn2. That would be the objective value, which upon simplification will give the following: CB times B inverse into B minus N1 xN1 minus N2 xN2 plus CN1 xN1 plus CN2 xN2. I simply copied XB, nothing else. And then this will give you CB B inverse B minus something times xn1. What is that something? CB B inverse n1 minus cn1. That's the multiplier for xn1 minus CB B inverse n2 minus cn2 times xn2. That's the, if you factor out everything that has to do with xn2, this is what you get in parentheses. This one? Yes. This is CB B inverse B. Yes. Thank you. That's CB B inverse B. Okay. So we defined the reduced cost vectors accordingly. R and 1 is what you see here, CB B inverse N1 minus Cn1. Similarly, R N2 equals CB B inverse N2 minus Cn2. This is the usual definition of reduced cost, or nothing new here. It's all the same. So this simply tells you that Z is equal to this constant CB B inverse B minus Rn1 xn1 minus Rn2 xn2. Okay? That's what we have. And my usual conclusion was, if you just view these dot products as summations, then that would tell you who to enter. Okay? So, but before I do that, let me just make a little bit change here. Let's just look at the differences here rather than. So let me just write the same thing. Let's subtract the lower bounds from the variables that are set equal to lower bounds. Okay? So xn1 is currently at the bounds. So I'm looking at the difference between the current value and the lower bound. Of course, the current value will be something more than the current value because they have to stay feasible. Similarly here. Except that I need to change that to plus, because I'm looking at the difference now for the upper bound, the variables that are at their upper bounds right now. They will be below the bounds, so there will be a non-negative difference here. So we're just looking at the differences between either the lower bounds or the upper bounds as long as, okay. But of course, when you make this, you need to make sure that you retain your equality. So how do I do that? There will be a Rn1, Ln1 here with a plus. So I have to subtract that. Okay. And there will be a plus Rn2. So I need to also subtract that one. Okay. So we added the same thing and then subtracted. We added and subtracted the same thing, so equality is retained. So this gives you CB B inverse B minus Rn1 Ln1 minus Rn2 Un2. I'm just taking these to the front, minus summation Rj xj minus lj, which is this one, okay? J in the index set R1, which refers to those variables that are set equal to their lower bounds, okay? And this part, Rj uj minus xj, for those variables that are set equal to their upper bounds. Now, how much is this, do you think? This is something that we did not do last time. I just gave an argument based on that. Nevertheless, this is, I think, more insightful. How much is that?
Z bar.
Z cap, yes. It is Z cap. Why is it that? Because, well, let's just work it out. This will be CB B inverse N1 minus Cn1, right? Ln1 minus CB B inverse N2 minus Cn2 minus the other stuff, Rj xj minus lj in R1 minus Rj uj minus lj, uj minus xj, j in R2. Now, if you look at this, I don't know, if you simplify it, what do we get here? we get, well, let's just do it. CB, B inverse into B minus N1, L1, right? And then from here, we get, there's something missing here. What is that? This is UN2. UN2, sorry. Yeah. From here, CBB inverse into N2, UN2. That's your B cap. Is it? It's supposed to be. Yeah, it is B cap. And then I also have CN1, LN1. And I also have, what do I have? CN2, LN2. Plus all the stuff here, which is simply Rj, Uj minus Xj, J in R2. So this is B cap, and this simply tells you CB, B inverse B cap plus Cn Ln1, Cn Ln2. That's exactly what we have. Okay? So this is simply equal to, so Z is equal to the current value minus, oh, I forgot the plus here. These are supposed to be plus, right? I changed it along the way. Okay, so Z cap minus Rj, Xj minus Lj for those non-basic variables at the lower bound plus Rj, Uj minus Xj for those variables that are at the upper bound. Where? That's U2, yeah. If you go too fast, that's what happens. When I was 27 years old, I was teaching at Georgia Tech. That was the first time I started teaching. Fresh PhD, you know, started teaching. And then I used to also do folk dancing. So somebody in the folk dancing one day told me that she is building a house. That was very interesting. You know, a single person with a child, a single mother. She was building a house. To me, that was very unusual because in Turkey, nobody builds a house just by herself. And then she said, well, I asked her, you know, how do you do it? You know, it's hard to build a house. She said, I built one piece at a time. You know, she's building the wall only one piece at a time, just, you know, one stone at a time or one brick at a time. So she built the wall of the house in 6 months, which is fine, but she did it. And she said to me, well, I work slowly but surely. And I ingrained it in my mind. If you work slowly and surely, it works. It really helps. But over here, of course, we work fast, and it's easy to make mistakes. So watch out. Thank you for pointing out the mistakes. Of course, the best thing is to work fast and accurately, but you know, sometimes we make mistakes. Okay, so this is the form of the new objective value, and this simply tells you that if you look at your non-basic variables that are currently at the lower bounds, if you increase them, if you look at the difference here, if this difference is positive, and if Rj is positive, that's really good because by doing so, you would make Z go down from the current value. Similarly, if you don't touch that, but look at these ones, so Xj is currently at the upper bound. If you decrease it from the upper bound, the difference will be positive here. that positive difference, there's something wrong here. What is it? I switched the sign somewhere. Did I not?
Yes, we were using minus for both.
How did I? Just a second. This is correct. This is plus. Oh, okay. So, definitely, yeah. This is correct. Nothing is wrong. So I want a negative Rj here. If Rj is negative, and this number in the parentheses will be positive if you go down, okay? So negative times positive will make you go down from the current value, okay? So we enter any xj from the first set as long as its Rj is positive, or any xj from the second set if its Rj is negative. But typically, what we do is we choose a variable k from the arguments of the maximum of the Rj's, j in R1, or I should say arg max of max, okay? Or the maximum of the negative Rj's. Rj's in the second set are supposed to be negative, okay? And so negative Rj is positive, j in R2. If the optimality criterion is not satisfied. What is the optimality criterion? The optimality criterion for a minimization problem is that you want Rj less than or equal to 0 for every j in R1. So nothing qualifies in the first set that can improve the objective value. And Rj is greater than or equal to 0 for every j in R2. That's your optimality criterion for minimization. So if this is not the case, then somebody in R1 will have Rj positive, in which case, of course, you look at the maximum such, or somebody in the other one will have negative, in which case you're looking at the negative. So as long as the maximum of the two max here is less than or equal to 0, your optimality criterion is satisfied. If one of them is positive, then k will be a variable to enter. So, suppose we decided to enter xk. Okay? So there are two cases here. Case 1, xk is currently at the lower bound. New value will be the lower bound plus some amount delta. You're increasing it by delta. Delta is positive here. Okay? All right. All xj in R1 other than k are still at their lower bounds, and all rj, sorry, all xj in the second set are still at their upper bounds. So you allow only one non-basic variable to become basic. Okay? In this case, xk will become basic. The other ones are still non-basic. So all of these other than k are still non-basic. The current basic variables are affected in what way? B inverse times B cap is the current value. Minus yk times delta, the increase upwards from the lower bound, is how it is going to affect your xb, where yk is how much? B inverse times ak, okay? As usual. Do you agree with me? Do you agree with this part? Well, let's look. So, let's just check, because I need to make sure that we're doing it correctly. What do we have? We have bxb plus bxn1, not bn1x1, xn1 plus n2 xn2 equals b. That's the kind of equations we have. And here, of course, we have bxb. Now, everybody here will stay the same, except we're going to allow one of them to change. So currently, these are all at the lower bounds. Only one of them will change. So in the current situation, we have this, except that, for example, from here, some variable will enter. So it will be ln plus whatever, the lower bound, plus delta. Okay? So that plus delta will pick up the appropriate column here. And of course, you take it then to the left, to the right side, then multiply it by B inverse. So this is correct. This looks quite correct. Okay? I'm not going to go through all the details, but only one column is affected, and obviously that's the situation. All right. So with that, we need to decide who will become non-basic. So let's just write it this way. XPI will be the current value. Is this B? That's not B inverse. B cap or B inverse? It's B cap. This is already B cap, sorry. That's already B cap. Okay. B cap gives you the current values of the basic variables. So that's how you've got that. So XPI is the current value minus the ith component of yk times delta. Okay? Now, when you look at this, when delta is going up from 0, depending on the sign of yik, things will either go down or up, or may stay the same if yik happens to be 0. Okay? So, which ones are the candidates? Let's just partition the index set 1 through m into 3 parts. Say, let's just call this I. Okay. Let's take I plus to be the set of indices I in I such that yik is positive. I minus set of I for which yik is negative, and I sub 0 set of I such that yik is equal to 0. Now, for those I coming from the first set, I plus set, what happens here? What kind of a change do I have? Well, yik is positive, delta is positive. Obviously, the variable is going down then from the current value. So these are the variables that may hit their lower bounds. Okay? So this gives you candidates to hit the lower bound because they are going down. The ones here will be increasing upwards from the current value, so they may hit upper bound. The ones here, they don't change, so we don't do anything about them. Okay? No change. The old value is still between the bounds by assumption, so we don't do anything with them. Okay. So, we need to compute, well, what do we, well, we want bi minus yik delta to be greater than or equal to the lower bound associated with the ith basic variable for those I in I plus. Okay? Because they may hit the lower bound. The other ones, we want the new value to be less than or equal to the upper bound for I in I minus. Okay? So, the first set of inequalities associated with I plus, if you solve for delta, let's call it gamma 1. Delta, if you keep it, let's see. Let me take, okay. Let me take this to the right side, yik delta to the right side. So we want a minimum ratio here, bi minus, bi cap minus lbi, and then divide by yik. I'm simply solving for delta. That's really nothing mysterious here. And when you solve for delta, you obtain a bunch of bounds on delta. Each bound is of this form. It's an upper bound on delta. And of these upper bounds, the smallest one is your critical one. Okay? So you choose the minimum such ratio. And you call that, say, gamma 1. That's the minimum ratio coming from here. And then you compute another ratio, gamma 2, for the second one. This one, yik is negative here. So minus yik is positive. So I'm going to keep it here. So delta will be less than or equal to u bi minus bi cap divided by yik minus yik. Minus yik is positive, so when you divide by minus yik, of course, the sense of the inequality does not change, and so you're looking for the minimum of them. So you compute that, and you get those ratios. And then you choose the minimum of either gamma 1 or gamma 2. You know, you've got a bunch of ratio. Well, you've got at least 2 critical values here. Whichever one is the smallest, that's how much you can change your delta. It may also so happen that before you hit one of these bounds, you may be actually changing the variable under consideration from the lower bound to its upper bound before anything of this sort happens. So you need to also look at the difference between UK and LK. Whichever is smallest here, that will be the critical value. So you're looking, so let's call that gamma. Gamma is the minimum of those numbers. Why we are looking at UK minus LK? The reason is the following. Okay, here are the possibilities. You're trying to increase xk, the entering variable, from its current value, which is at the lower bound, to something more than the lower bound. Okay? And delta is the amount by which you move from the lower bound. So when you start increasing it, you get a reduction in the objective value. So you want to increase it as much as you are permitted by the feasibility conditions. Okay? When you start increasing it, one of 3 things could happen. Number 1, some basic variable may go down sufficiently to hit the lower bound. That's the case when gamma 1 is smaller than gamma 2. Okay? Number 2 possibility, some basic variable may start increasing and finally hit its own upper bound. That's the second possibility when gamma 2 is smaller than gamma 1. Okay? But the third possibility is before any of the basic variables can hit their either lower or upper bound, delta is actually delta changes from delta is large enough to make the new variable hit the upper bound. That's the third possibility. Okay? Does that make sense? Well, of course, that's so you're trying to increase it, but before anything happens with the current set of basic variables, you actually move from the lower bound to the upper bound. So in the last case, of course, if this is the case, your current non-basic variable, which is xk, currently it's non-basic, it will be also non-basic in the new solution, but it used to be in the lower bound. Now it will be at the upper bound. Okay? So here are the possibilities. Of course, in the last case, I'm going to assume that this is strictly less than the minimum of gamma 1 and gamma 2. So, if UK minus LK is less than the minimum of gamma 1 and gamma 2, then xk simply switches from lower bound to upper bound before any of the basic variables can become non-basic. Okay? So in this case, xk stays non-basic, but now it is at its upper bound, whereas it used to be at the lower bound. Okay? And the first two cases, xk becomes basic. And one of the basic variables, depending on which of these two cases occurred, becomes non-basic. Some xbi becomes non-basic. Okay? So let's elaborate on that. So let's assume gamma is less than UK minus LK. It's realized by either gamma 1 or gamma 2. And we update the variables. xbi, the current value or the new value, will be the old value minus yik times delta gamma. Gamma will be the new value you assign to delta. So gamma is the minimum ratio here. Okay? And that's going to be the new value of xk. And that's how it affects the old variables. This is, of course, true for every I other than the ratio that gives you the minimum. Where R is the index for which some basic variable xbr hits either its lower bound or its upper bound. Okay? All right, so for every variable other than the rth one, these are the new values of the basic variables. These are still basic. xbr becomes at the lower bound if gamma is happen to be equal to gamma 1, for which the ratio is BR cap minus LBR divided by YRK. So if gamma is realized by gamma 1, a minimum ratio coming from the plus set, then XBR, of course, goes to the lower bound and becomes non-basic now. Okay. On the other hand, it will become still non-basic, but at the upper bound, if it so happens that gamma is realized by gamma 2, for which the smallest ratio is, what is it, U BR minus BR cap divided by minus YRK. That's the minimum ratio in the second case. Either way, XBR becomes non-basic. For J in R1 union R2, the set of non-basic variables, except the entering one. In that case, xj is still at the lower bound for j in R1 other than k, and xj is at the upper bound for j in R2 other than k. There's only one variable that remained. These are still non-basic. Now, xk is now basic. You entered it, and it actually will be basic. How much is it? LB, the LK, the lower bound, plus delta, which in this case is gamma. That's how much you increased it. Okay? Boy, doesn't it sound complicated? The idea is simple, but you know, too many details to pay attention to. Other than that, there's really nothing difficult about it. Okay? We haven't. This is only for one case. This is the assumption. Okay, so let's take a 10-minute break. Then for the remaining cases, it will be similar. So we'll just write it down, okay? 10-minute break.